Chapter 25, Statistical Thermodynamics, Section 25.7, Entropy. For a system that contains n distinguishable particles, which occupy m energy levels, assuming the Boltzmann distribution, the total number of microstates is given by this formula. W is equal to n factorial over a1 factorial, a2 factorial, a3 factorial, etc., all the way to a sub m factorial. N is the total number of particles in the system. A sub I is the number of particles in the ith energy level. So a sub I over n is equal to e to the power of negative beta epsilon I over the sum of e to the power of negative beta epsilon I. And we define the partition function q to be the sum of all those exponential functions. Therefore, a sub I over n is equal to e to the power of negative beta epsilon I over q. If we sum up all those a sub I over n, the sum would be 1. The probability of a particle occupying the ith energy level is denoted by P sub I. P sub I is equal to a sub I over n. P sub I is equal to e to the power of negative beta epsilon I over q. The occupation number of the ith energy level is n times pi. N times pi is also denoted by a sub I. Now let's look at Boltzmann's entropy equation. Boltzmann's entropy S is equal to the Boltzmann constant K sub B times the natural logarithm of W. W is the total number of microstates accessible to the system. Therefore, the Boltzmann entropy of this n-particle system is this. S is equal to K sub B times the natural logarithm of n factorial divided by a1 factorial, a2 factorial, a3 factorial, etc. And again, we're going to use the number of microstates associated with the Boltzmann distribution to evaluate W. So Boltzmann entropy is equal to Boltzmann constant K sub B times the natural logarithm of W. And W is the number of microstates. W is equal to n factorial over a1 factorial, a2 factorial, etc. a1, a2, a3, all the way to a sub m can be determined assuming the Boltzmann distribution. Now we can separate these two terms. So over here we have logarithm of something divided by something else. It becomes subtraction. So we have kb times the logarithm of n factorial minus the sum of the logarithm of ai factorial. So the logarithm of a product is the sum of different logarithms. Now let's use Stirling's approximation, which is ln x factorial is approximately x times ln x minus x. Now we replace this ln n factorial with n times ln n minus n. We replace every single ln ai factorial with ai ln ai minus ai. So we have the expression of entropy expressed this way. Now we noticed the sum of ai is n. So we have minus n here, we have minus negative n here, they cancel. Therefore we have only two terms left. It's going to be the Boltzmann constant multiplied by this, n times ln n minus the sum of ai ln ai. Now I'm going to expand this n. N is equal to the sum of ai. So I replace n with the sum of ai here. I just copied the second sum here. The reason is I like to combine these two sums. So after I combine these two sums, I get negative kb times the sum of ai ln ai over n. So if you just look at this, it's going to be the logarithm of n over ai. But I put a negative sign here. So now it's the logarithm of ai over n. Remember, ai over n is the probability of a particle occupying the ith energy level, denoted by pi. So ai over n is just pi. And ai is simply n times pi. Now we get this expression. I can take this uppercase n out of the sum because this n does not depend on I. Now we have this equation, and we can combine this n and kb because kb is the gas constant divided by the Avogadro constant, and the number of particles is the number of moles times the Avogadro constant. Therefore, we can rewrite this part as negative ni, nr. And if we look at the sum, it's a very simple expression. It's the sum of pi times the logarithm of pi. Therefore, the Boltzmann entropy is equal to approximately negative nr times the sum of pi ln pi. Pi is the probability of a particle occupying the ith energy level. Pi is ai over n. Pi is e to the power of negative beta epsilon I over the sum of e to the power of negative beta epsilon I. Pi is e to the power of negative beta epsilon I over q, where q is defined to be the sum of e to the power of negative beta epsilon I. Q is multiplicative, so Q is equal to the product of the translational partition function, rotational partition function, vibrational partition function, and electronic partition function. Epsilon, or the energy of a particle, is additive. The energy of a particle is its translational energy plus its rotational energy plus its vibrational energy plus its electronic energy. So over here, entropy is also additive. So the entropy of a system is equal to the total translational entropy plus the rotational entropy plus the vibrational entropy plus the electronic entropy. In general, the translational entropy is greater than the rotational entropy. The rotational entropy is greater than the vibrational entropy. The vibrational entropy is greater than the electronic entropy. Because P sub I depends on the relative energies of the particles, we can simplify the expressions of the vibrational partition function and electronic partition function by have some zero reference. We can define the 0K or 0 Kelvin internal energy as the zero reference. For convenience, the 0K internal energy, which is the sum of the electronic energy and the 0 point vibrational energy of the molecule, is just set to 0 when computing the partition functions for vibrations and electronic partition function. Again, Q is translational Q times rotational Q times vibrational Q times electronic Q. We have derived the translational partition function, which is 2 pi m kBt to the power of 1.5 times the volume of the container over the Planck constant cubed. We derived the rotational partition function for a linear molecule, which is kBt over sigma hcb. B is the rotational constant, and sigma is the symmetry factor. If the linear molecule has an inversion center, sigma is 2. If the linear molecule does not have an inversion center, sigma is 1. So if you have a d infinity h point group, sigma is 2. If the point group is c infinity v, sigma is 1. What if we have nonlinear molecules? Well, then we have 3 different rotational constants, b1, b2, and b3. The rotational partition function for a nonlinear molecule is the square root of pi over sigma, Again, sigma is the symmetry factor. Now multiplied by kBt over HCB1 to the power 1/2, kBt over HCB2 to the power 1/2, kBt over HCB3 to the power 1/2. So the essential difference between linear and nonlinear is this. For a linear molecule, its Partition function is proportional to t. For a nonlinear molecule, its Partition function is proportional to t to the power 1.5. Now let's choose the 0k internal energy as the zero reference. More specifically, we're going to choose the lowest electronic energy as the zero reference. We're going to choose the 0-point vibrational energy as the zero reference, and therefore the electronic Partition function is simply G sub 0. This is just the multiplicity of the ground electronic state. And over here, we also assumed that the excited states do not make any contribution to the electronic Partition function. This approximation is very accurate as long as the electronic energy spacing is much greater than kBt, and that's usually true. For a linear molecule, we have 3n-5 vibrational modes. For a nonlinear molecule, we have 3n-6 vibrational modes. So we have the vibrational Partition function as the sum of 1 over 1 minus e to the power of negative h nu I beta. For 3n-5 modes for a linear molecule, or 3n-6 modes for a nonlinear molecule. Again, a nonlinear molecule contains 3 rotational modes. A linear molecule contains only 2 rotational modes. And that's why we have a difference here and here. Now let's look at the derivation of Boltzmann's entropy. So previously we have entropy equals negative kBn times the sum of pi ln pi. So we can keep deriving this by replacing p sub I with e to the power of negative beta epsilon I over q. So over here pi is this, pi is replaced with this as well, e to the power of negative beta epsilon I over q. Now expand this. This is simply the logarithm of the top minus the logarithm of the bottom. The logarithm of the top is negative beta epsilon I. The logarithm of the bottom is just minus ln q over here. So we have this expression. We see negative sign, negative sign, negative sign, they cancel. So we have n times kb over here, and then q is independent of I. So I'm taking q out of the sum. So divided by q, and then the sum of this exponential function, e to the power of negative beta epsilon I times beta epsilon I plus ln q. Now we separate these two sums, and n times kb is just nr. So we replace n times kb with nr. And now let's look at the first term. The first term is beta over q over here, and then the sum of epsilon I times e to the power of negative beta epsilon I. The second term, ln q, is independent of the dummy index I. So I take ln q out, ln q over q, and then we have the sum of this. Now look at the sum of e to the power of negative beta epsilon I. This is simply q by definition. The partition function q is defined to be the sum. So these two cancel, we have ln q over here. What about this one? I'll just copy this sum over here. It's beta over q times the sum of epsilon I times e to the power of negative beta epsilon I. And because q is the sum of this exponential function, previously we derived dq over d beta, which is negative sum epsilon I times e to the power of negative beta epsilon I. So really this sum is equal to negative dq over d beta. And now let's look at a little bit more derivation. Let's look at this t times d ln q over dt. Well, it's equivalent to kBt times dq over q over dkBt. How did I get this? Well, I simply multiply this t by kb and this t by kb. Kb and kb can cancel. d ln q is dq over q. Why is that? It's just because d ln q over dq is 1 over q. Therefore, dlnq is dq over q. So we got this. kBt is 1 over beta. kBt is 1 over beta. Well, that's just the definition of beta. Beta is defined to be the reciprocal of kBt. Now we have this expression over here, and then what is this? D 1 over beta. It's this one is negative 1 over beta squared d beta. So we can clean up everything. We get negative beta dq over q d beta. It sounds really complicated, but if you look at this, this is equivalent to this or this. Why is that? Because dq over d beta is negative sum of epsilon times exponential function, right? So I'll just replace this dq over d beta with this whole thing. There's a negative sign here, they cancel. And then you have beta over q. We copy that here, and then we copy the sum here. So now you can see beta over q times the sum of epsilon I times e to the power of negative beta epsilon I is t ln q over dt. So this whole thing, I was just proving this is equal to t times ln q over dt. This part can be replaced with t times d ln q over dt. So Boltzmann entropy is nr times t times d ln q over dt plus ln q. The molar entropy of the system is r times d ln q over dt plus ln q. We can even further simplify this. If you know d ln t is dt over t, we'll get an even simpler expression for the molar entropy. Molar entropy is equal to r times this sum, the sum of d ln q over d ln t and ln q. So it's not just ln q, also it's the slope of ln q versus ln t. You have two components here that make contribution to the molar entropy. So why do we have this? Again, it's just because d ln t over dt is 1 over t, and then we have this. Over here we have the equation for the molar entropy. It's r times t times d ln q over dt plus ln q. And this part can be written as d ln q over d ln t. This is based on one assumption. We assumed all particles are distinguishable. But what if the particles are indistinguishable? In that case, the total number of microstates must be divided by n factorial, because for each combination of n particles, there are n factorial identical permutations. And all these n factorial permutations correspond to a single combination. For example, if 3 distinguishable particles occupy 3 different energy levels, and then you have a total of 6 possible arrangements. The number of microstates is 6. However, if the 3 particles are indistinguishable, let's say they are AA and A, they occupy 3 different energy levels, and then there's only one arrangement. We can say there's A in energy level 1, there's A on energy level 2, and there's A on energy level 3. And that's just one microstate. Therefore, when the particles are indistinguishable, we need to divide the number of microstates by n factorial. So the entropy should be reduced by this much accordingly. Now the expression for entropy is nr times t times d ln q over dt plus ln q minus kb times the natural logarithm of n factorial. So it's just this part should be reduced correspondingly. And now we have this formula. Why do we have this? Well, it's just Stirling's approximation. Ln n factorial is n times ln minus n. And then we have a negative sign here, so we swap those. And then the uppercase n times kb is the lowercase n times r. Kb is r divided by the number of divided by Avogadro constant. And this n is the number of moles times the Avogadro constant. Now let's look at the molar entropy in more detail. The molar entropy is R times T times ln Q over dt plus ln Q plus 1 minus ln of the number of particles. Now we're going to separate this whole thing into 4 parts. The translational entropy, the rotational entropy, the vibrational entropy, and the electronic entropy. The indistinguishability goes in here for the translational modes. Right, again, we have molar entropy equals to R times this whole thing that can be separated into the translational entropy, rotational entropy, vibrational entropy, and the electronic entropy. Again, Q, the partition function of a molecule, is the product of the translational partition function, rotational partition function, vibrational partition function, and electronic partition function. The translational partition function is 2 pi m kBt to the power of 1.5 times the volume divided by the Planck constant cubed. For linear molecules, the rotational partition function is kBt over sigma hcb. Sigma is the symmetry factor, b is the rotational constant. For nonlinear molecules, the rotational partition function is square root of pi over sigma times the square root of kBt over hcb1, the square root of kBt over hcb2, the square root of kBt over hcb3. If we choose the lowest electronic energy as the zero reference, electronic partition function is just G0, the spin multiplicity of the ground electronic state. If we choose the 0-point vibration energy as the zero reference, then the vibrational partition function is simply the product of 1 over 1 minus e to the power of negative h nu beta. For a linear molecule, we have 3n minus 5 different vibrational modes. For a nonlinear molecule, we have 3n minus 6 different vibrational modes. For an ideal monatomic gas, the rotational partition function is 1. The vibrational partition function is also 1. We just do not have rotations or vibrations. And therefore, the monatomic gas possesses only the translational entropy if the electronic partition function of this atom is just 1. So, for example, if you have helium, argon, xenon in the ground state, those atoms have a spin multiplicity of 1. So G0 is just 1. Therefore, the electronic partition function is 1, assuming the energy spacing between the ground and excited electronic energy levels are much greater than kBt. And now we have only translational entropy. The equation is this. The first 2 terms are the molar entropy for distinguishable particles. What if you have indistinguishable particles? For example, if you have a bunch of helium atoms, they're indistinguishable. We need to make a correction. We need to have the molar entropy for distinguishable particles and then minus kb times the natural logarithm of n factorial. So therefore we see this here. The translational molar entropy is therefore this, after we replace the translational partition function with its expression here and here. This part is easy because we're taking the derivative of this function with respect to temperature, and this logarithm can be decomposed into the sum of 2 different logarithms. The first one is the logarithm of t to the power 1.5. The second logarithm is something independent of temperature. And then we can take the derivative, which is just 1.5 divided by t, and then multiply by t here, so it's just 1.5 over here. This part, we'll just copy it here, and then plus 1, and then minus ln n. N is the number of particles. Again, this derivative, this whole derivative is 1.5 divided by t, and then multiply by t here, you get 1.5. Now let's do some cleaning up here. 1.5 and 1, it's 2.5. And I see logarithm of v minus logarithm of n. I put them here. And then I see this 1.5 times the logarithm of 2 pi m kbt over h squared. So h squared to the power of 1.5 is h cubed. So from here to here it's just algebra. Now we have the translational entropy. The translational entropy is just n times the molar translational entropy. It's just n times r times everything inside the square bracket. 2.5 here, the logarithm of v over n, so, and then 1.5 times the logarithm of 2 pi m kbt over h squared. Using this equation, we can prove some equations in thermodynamics. In thermodynamics, we learned how to compute the entropy change in an isothermal expansion, going from initial volume to final volume. The entropy change of the ideal monatomic gas is this: final minus initial, and then we examine this. Only the term in the middle depends on volume. The other terms, they cancel, so we have this minus this, and therefore the result is nr times the logarithm of v final over v initial. We were able to prove this in thermodynamics. Now let's look at an isochoric process. So from T initial to T final. Now again, let's examine this term, they do not depend on temperature. Only here we have 1.5 times the logarithm of T. Alright, so we have 1.5 times the logarithm of T final, 1.5 times the logarithm of T initial, and then multiply by nr here and here. The result is 1.5 nr times the logarithm of temperature ratio. It turns out for monatomic gases, 1.5 nr is the value of C sub v. So the entropy change is C sub v times the logarithm of the temperature ratio. We also proved this in thermodynamics. So again, starting from this equation, in statistical thermodynamics, we can prove equations in thermodynamics, like this too. We can predict the standard molar entropy of ideal monatomic gases at room temperature, and actually any other temperatures or any other pressures. We just need to plug in numbers. First, this is the expression for molar entropy right here, and then V over N is RT over P over Avogadro constant. It's just because the uppercase N is the number of moles times the Avogadro constant, and then we know PV equals RT. We keep this equation here, so we just change V over N is equal to RT over P times Avogadro constant on the bottom. We can make it a little easier to calculate numerically because this m is the mass of just one particle, and Kb is a very small number. So I'm gonna just multiply this m by Avogadro constant. I'm gonna multiply this Kb by Avogadro constant. So this lowercase m becomes uppercase molar mass, and this Kb becomes R. And don't forget to divide the Avogadro constant twice on the bottom. Now we have this equation. Further, we can separate this T out because I see a LNT here and 1.5 LNT here. So we copy 2.5 here. We have logarithm of R over P times Avogadro constant over here. We have LNT plus 1.5 LNT. Well, now we have 2.5 LNT, and then we have 1.5 times the logarithm of 2 pi mr over Na squared H squared. So if you look at this equation, you can see the molar entropy depends on pressure and temperature. When we have higher temperature, higher molar entropy, higher pressure, lower molar entropy. Again, this uppercase M is the molar mass, but it has to be in kilogram per mole. If you try to do numerical calculations, it's easier to just use SI units. Now let's calculate the molar entropy for helium at room temperature and 1 bar. We plug in all the numbers. So it's R times the sum of 4 terms, 2.5, the logarithm of R over P in A, 2.5 times ln T, 1.5 times ln 2 pi mr over Avogadro constant squared h squared. So we plug in all the values. R is 8.31446, 2.5 here, logarithm of R over the pressure and Avogadro constant, 2.5 times the temperature, and then 1.5 times 2 pi times the mass in kilogram per mole times R divided by Avogadro constant squared and h squared. All numbers are in SI units. So in the end, I just get SI units. I get 126.1 joule per mole per Kelvin as the molar entropy for helium at room temperature and 1 bar condition. The molar electronic entropy is R times the logarithm of G naught, because the electronic Partition function is approximately G naught. G naught is just 1 for helium. So if we look at the molar entropy for the electronic energy levels of helium, it's 0. Mostly it's because all helium atoms are in the ground electronic state. I think 99.9999999% of helium is in the ground electronic state. And therefore the entropy is just 0 regarding its electronic distribution. The electronic entropy of helium is simply 0. Usually if you look at any other chemical with a singlet ground electronic state, its entropy is usually just 0. Unless, with rare exceptions, this chemical has some excited states only slightly above the ground electronic state. Now let's look at some molecules. When we look at molecules, we have translational modes, rotational modes, vibrational modes, and electronic modes. This part is usually 0, but for completion, so we still include these 4 terms here. Now let's look at HCl, for example. Let's say HCl35. We can calculate its molar translational entropy. It's 153.5. The calculation is a little interesting here. I'm comparing the translational entropy of HCl with the translational entropy of helium. There's a reason I do this. Let's go back to the previous page. Okay, now if you look at this equation, you can see between HCl and helium, if you compare HCl and helium, the only difference is this M. Also, if you look at this equation, same thing. The only difference is this molar mass between helium and HCl. So they should just differ by like 1.5 times the logarithm of mass 1 minus the logarithm of mass 2, and then multiplied by R. That's it, because all other terms are the same. If we're looking at the same temperature, room temperature, 1 bar condition. Look, 1 bar condition, same temperature, they only differ by molar mass. And our plugging 1.5 ln molar mass here, 1.5 ln molar mass for helium, we got the difference. So the difference is 27.4 joule per mole per Kelvin. So the molar translational entropy of HCl is greater than the molar translational entropy of helium, only because HCl is heavier. And again, why is that? Since HCl is heavier, the translational energy spacings are smaller for HCl. So you can have a kind of more wild distribution of those molecules in more translational energy levels in HCl. Now let's look at the translational molar entropy of HCl. It's 27.4, more than helium. So I sum it up, I got 153.5 joule per mole per Kelvin. Now let's look at the rotational entropy. Here's the equation. We're going to just use this equation over here. dlnq over dt is simply 1 over t. And 1 over t times t is just 1. So there's only 1 here. And over here, the rotational Pauling function is kBt over hcb. The symmetry factor sigma is just 1 because this molecule does not have an inversion center. So hcb is h bar squared over 2I. I is the moment of inertia, and I is mu r squared. So we have all these equations. H bar is h over 2 pi. So that's why you see a bunch of pi on top. And now we can just evaluate this. Before we do this, this mu is m1 m2 over m1 plus m2, lowercase m. I want to convert it to uppercase m, so we multiply this mu by Avogadro constant, and then that's why you see Avogadro constant on the bottom. And also there's a kb. I want to replace that with r, so you have a second Avogadro constant here. Now we can just plug in all the numbers to get the rotational molar entropy for HCl. It's just R is 8.3 and then 8 pi. The molar mass for hydrogen is 0.001 kilogram per mole. For chlorine, I think it's 0.035 kilogram per mole. Plug those numbers in. The equilibrium bond distance, you can look it up. It's 1.275 angstroms. Plug it in. Plug in R. Plug in temperature, assuming we're talking about room temperature. And we can do the calculation. You get 33 joule per mole per Kelvin. So we've got translational entropy. We got rotational entropy for 1 mole HCl. What about the vibrational entropy, electronic entropy? First, let's look at the vibrational entropy. First, let's use the 0 point vibrational energy as a zero reference. The molar vibrational entropy of HCl at temperature T is this. It's really complicated. It's R times T times dlnq over dt plus lnq. And we can evaluate this. We'll put negative sign here so that we can flip this up. We can flip this up. Now we take the derivative, the logarithm of something. It's going to be the reciprocal of this. And then we use chain rule. What's the derivative of this? You have this function over here. And then what's the derivative of this? You get something here. Alright, and then we clean it up. From here to here, it's just algebra. From this term to this term, we just multiply both the top and bottom by e to the power of positive h nu kBt. And then we got this minus 1 on top. This just disappears. We have t over t squared, so it's going to be just kBt over here. And then we copy the logarithm here. Why negative? Okay, it's just negative, negative, you get positive, negative, positive, you get negative. We can see h nu over kBt everywhere, here, here, and here. So it's a lot easier if we pre-calculate at least h nu over kb. Alright, h nu over kb is this, hc over lambda over kb, and this is 1 over lambda. You plug in all the numbers. H nu over kb is 4,200. And actually this has a unit. The unit of this is Kelvin. Sorry about missing the unit. It's actually in Kelvin. And usually for a unit we use regular font. We use italic font for variables. Now at room temperature, we have this h nu over kb divided by room temperature. We get roughly 14. and this is unitless. Now I'm going to plug in 14 here, e to the power 14 minus 1, logarithm of 1 minus e to the power of negative 14. So we get this expression. We don't even have to calculate this because e to the power 14 is huge. 14 over that, it's really small. And this part is really close to Ln1, and Ln1 is 0. Therefore, the vibrational molar entropy for HCl is just 0. The molar vibrational entropy for this molecule at room temperature is this. It's roughly 0. This result is expected because nearly all HCl molecules occupy the same lowest vibrational energy level at room temperature. So more than 99.9999% HCl occupy the lowest vibrational energy level. There's really no disorder. Therefore, the molar vibrational entropy is just 0 or very close to 0 at room temperature or even higher temperatures. Usually you can say it's 0 unless the temperature is really high. On a side note, for molecules with low vibrational frequencies such as CO2 at room temperature, h nu over kBt is only 2.7. So remember, for HCl, h nu over kBt is 14, but for chlorine 2 at room temperature it's only 2.7. And in this case, the vibrational entropy can be more significant. We'll just replace 14 with 2.7. We get this formula. It's roughly 2.2 joule per mole Kelvin. It's still small. It's smaller than the translational and rotational entropy, but if you really want accurate molar entropy for chlorine 2, you probably want to take this 2.2 into account. The molar electronic entropy of HCl is 0 because pretty much all HCl molecules occupy the same singlet ground electronic state. So G0 is simply 1. The multiplicity of a singlet spin state is just 1. Singlet means 1. In total, the molar entropy of HCl 35 at room temperature and 1 bar pressure is this. The molar translational entropy, the molar rotational entropy, and then we have vibration and electronic. These two are just 0 for translation. We have this number. For rotation, we have this number, 33. So in total, we have 186.5 joule per mole per Kelvin. Now, why do I specify chlorine 35? Because if you use chlorine 37, well, you will get the slightly higher translational entropy and a slightly higher rotational entropy as well. So this number is for chlorine 35. For chlorine 37, you'll get a slightly higher molar entropy. Now the literature value of the entropy of HCl is 186.9. Look at these two numbers. They are pretty close to each other. These two numbers are obtained for room temperature and 1 bar pressure. 186.5 is our theoretical calculation. 186.9 is the experimental value. Theory and experiments agree with each other.
I didn't get that. Could you try again?
Similarly, we can hand calculate the molar entropy of any gas. And we can even calculate the molar entropy of a liquid or solid, given their partition function. For liquid or solid, it's hard to predict the molar entropy because it's a little hard to get the partition function right. In a liquid or solid, every single particle feels attraction and repulsion from surrounding particles, and it's hard to get the potential energy right. But if you do have the Q, you can hand calculate the molar entropy even for liquids and solids using this equation. Again, the molar entropy is simply the sum of 4 components: translational, rotational, vibrational, and electronic. Given the ideal gas approximation, the translational partition function is this: 2 pi m kBt to the power 1.5 times the volume of the container over Planck constant cubed. With the rigid rotor, that means the radius is constant. Rigid rotor approximation, harmonic oscillator approximation, that means the vibrational energy levels are n plus 1/2 times h nu, and that means the 0-point vibrational energy is 1/2 h nu. We can get the partition functions for rotation and for vibration. Rotation is here. If you have a linear molecule, it's kBt over sigma hcb. Sigma is the symmetry factor. B is the rotational constant. For a nonlinear molecule, it's square root of pi over sigma. We didn't derive this. Times the square root of kBt over hcb1, the square root of kBt over hcb2, times the square root of kBt over hcb3. For a linear molecule, we have 3n minus 5 vibrational modes. For a nonlinear molecule, we have 3n minus 6 vibrational modes. And the partition function is simply the product of 1 over 1 minus e to the power of negative h nu sub I times beta. So this nu sub I is the frequency of the ith vibrational modes. The electronic partition function is approximately G0. G0 is the degeneracy of the ground electronic state. The value of G0 depends on the electronic state. If you just have like helium, neon, H2, nitrogen 2, G0 is just 1. But if you have a doublet ground electronic state, G0 is 2. For oxygen gas in air, well, it's actually a triplet electronic state. So G sub 0 is 3.